Unit 1, Day 2, Precalculus notes. This is the first time we're going to try out this new camera system. Hopefully you like it. So let's get right after. This is pretty lengthy set of notes, so I guess this is as good a time as any to try it out. All right, we're starting right off here. Applications of the functions that we looked at. You know, what makes a relation a function? We talked about the vertical line test. We also said that for every x coordinate, there is only one y coordinate. If I say what is the y value when x is, say, 3, if you give me more than one answer, that's not a function, okay? When x is 3, there can only be at most one y coordinate. One input gives you one output every single time. Okay, so the graph represents the height, h, of a projectile after t seconds, okay? So the time in seconds is your input, your x coordinate. They put it on the x-axis. Your height in feet, your h, is going to be your output. It's on the y-axis, right? So question A says, explain why h is a function of t. Right? Why can we say h of t? Because if we substitute a time in, we only get one height. Right? So, for example, if we did the vertical line test, we never get two intersections. We know that each t yields only one h. Right? For example, at this point right here, 1.5 for t yields 30 for h. Right? So that's why h is a function of t. It's a relation that passes the one-to-one test as far as 1h for every 1t, okay? And also, you could say it passes the vertical line test, okay? So different things you could use to justify why h is a function, not just a relation, t. Okay, B says approximate the height of the projectile after 0.5 seconds and after 2.5 seconds. So 0.5 seconds is right here. 2.5 seconds is right here. So if we go up to our graph, okay, at 0.5 seconds, right, it's tough to see here, but on your notes, you can see some grid lines, right? And it's at the third grid line between 10 and 20. So because there are 4 in between, each one is worth 2.5. So this would be 12.5, 15, 17.5, and then 20, right? So the answer is at 0.5 seconds, the height of the object is 17.5 feet. Now, if you go over here to 2.5 seconds and you go up to your graph, right, it's actually on the same horizontal grid line that's on your notes. So, in fact, the same height is where the object can be found after 2.5 seconds. You know, if you can imagine, you know, you throw an object up in the air, at one point in time, it's at this height on the way up, and then at another point in time, it's at the same height, but it's on the way down. Okay, so it would make sense to have a real-life application where the object is at the same height 2 different times if you're throwing it or projecting it upwards, and then it has to come back there. Okay? All right, so it says approximate the domain of h. Remember, domain means all of the x coordinates, all of the input values. So since time is on your x-axis, it's all of the t values. So how far left and how far right does this graph go? Well, the graph goes as far as right here, because think about it, in real life, time in seconds does not go to the left of 0, right? Therefore, we start at 0, and it includes 0 for our domain, okay? So for our domain, we say for t has to be from 0 all the way to this point. This is how far right it is. Okay? And so looking at the grid, right, we'll say that this is 3.15. Okay? So from 0 to 3.15. And it includes both. So once 3.15 seconds has gone by, the object is already back on the ground. Right? So therefore, the function is over. It starts on the ground, goes up, it comes down, it's not on the ground, it's now on the ground. So the function begins and ends. It begins here at 0, okay? And it goes all the way to 3.15 seconds. That is your domain. Those are your x values, or in this case, the t values. And then, interesting little question here, d. Okay? We said h is a function of t, because t is your independent, your x coordinate variable. Is t a function of h? Could h be the independent variable? That would mean we'd have to turn our graph sideways so that the h is the horizontal axis and your t is your vertical axis. Well, if you turn it sideways, that means that the vertical line test we did before would actually be a horizontal line test. So visually, you can see that it's not a function if you turn it on its side. Also, we figured out right here, it can't be a function because at these two different h's, excuse me, the same h twice has a different time. So if I say h is 17.5 feet, what is the time? You give me two answers. You could say, oh, it's 0.5 seconds, or it could be 2.5 seconds. So the fact that I could give you two answers for t with one h tells me it's not a function of h. Okay, t is not a function of h. Okay, let's proceed. All right, they give you a nice little graph here, and they're asking you to find the domain and the range of this graph. Okay, nice little explanation here on the side. Okay, let's try to make this as simple as we can. Domain is how far left to how far right, and are there any gaps in between, any breaks? So the domain, right, and it gives it to you here, but the domain, how far left do we go? Well, we go as far left as that point right there, and it's an open circle. So it doesn't include that point. It doesn't equal that x coordinate, but that is where it starts. Okay? Where is that point? Well, it tells you both here and here. This is -2, -8. So how far left does that go? It goes as far left as -2. Right? But it's an open circle, so it does not include the -2. How far right does this graph go? The furthest right you have is this point right here. And it says that this point is 3,27. So how far right is that? It's at 3. Now, why is this a bracket and not a parenthesis? Because that is a filled in circle. This one over here is an open circle. So since it includes that point, we put the bracket there. Okay? It's really that simple. And because if we go from left to right, there are no x values that are not covered between here and here. Okay? There's no gap in between. All the x values are accounted for. Okay? So that's why this right here is the domain of f. And then the range we have said is the y values. Y values low to high. What's the lowest point that we have? The lowest point is at -2, -8. That's how far down it goes. So we're talking about the y values. So -8 is the lowest y value. Meanwhile, the highest y value is right here at 27. And once again, the point with the 27 has a bracket, and the point with the -8 has a parenthesis because of the open circle versus the closed circle. Okay, I'm not going to dwell on that one anymore. Let's continue to the next little section here. Okay, don't get nervous about the piecewise function. Don't get nervous because it looks a little different than maybe what you're used to. We're still going to say how far left, how far right, and are there any breaks? So for the domain, okay, we want to say that X is a part of what interval or intervals? Well, how far left does this go? There's an arrow. So it goes all the way to negative infinity. Always put a parenthesis with infinity and negative infinity. Okay, so we started negative infinity, so that's far left. We're going to start moving to the right. Here we go, we're moving to the right. Now at this point right here, it's open here, but this x coordinate at -1, it's still counted because there's a closed circle right above it. So all of these x's are included. Still, this x is included. We're going along. There's a closed circle right here. Bounces down to this open circle. We're still going to the right. We're still going to the right. We're still going to the right. And now there's an arrow. So from negative infinity to infinity, there are x coordinates accounted for with real numbers. Okay, so the domain is all reals. Okay, there is no x value that is not going to give you a real number y coordinate in this function. Okay, let's look at the range. Let's go with a different color for range. Jazz it up a little bit. Range. Okay, so look for y's. Okay, range is y values. How low to how high? What's the lowest we go? Let's see. This is pretty low. It's down at -2, but look at this. It's got an arrow. This goes down negative infinity. All right, so we go negative infinity. That's how low we can go. Give you a better look at infinity, maybe. So that's how low. We're going to go down to up. Okay, so we're going up, up, up. Still going up, up, up. These are still up points. Oh, right here. Okay, so right here at +1, that's as high as we go. There's a closed circle here, and there is a curve that touches +1. 1 is as high as it goes. Now, what you say, what about this over here? It doesn't matter. I mean, the question was, which y coordinates are included? Okay? This y coordinate's included here, we already got it. Right? So we go from low to high. What y coordinates are included? So it goes as low as negative infinity, and it goes as high as +1. Does it include it? Yes, it does. Bracketology right there. Okay? So it does not go above what? This function has a maximum. Okay? A maximum at 1. Okay. Question 2, another piecewise function. Right? Again, it looks a little funky, but let's just look at the domain and then the range. So for the domain, the x's. What x's are included? How far left does it go? All right, keep going. Oh, this is as far left as it goes, right here. Now there's an open circle, and it's at -2. Okay, so at -2, there's an open circle, parenthesis. So now we start going to the right. First interval. Okay, we're going to the right, 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 going to the right. Okay, we come right here. It's an open circle. We jump down here. Uh-oh. It's another open circle. So that means this x coordinate, which is 1, the x coordinate 1 is not part of our function. So the -2 went right until we hit 1, but it doesn't include 1. So is there another interval where we're going further to the right? Yes, there is. So we have to say there's another interval. Let's change the color on this interval. So we start at 1, but it doesn't include 1 because that's an open circle again. And now we're going to go to the right. We're going right, 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 right. And now there's an arrow. It says we go to the right forever. Right? So that is going to be positive infinity, or just infinite. So this is my domain. It goes from -2 to 1, but doesn't include 1. And then 1 to infinity. 2 intervals. For my y coordinate, my range, how far down to how far up? So again, we're looking at the y-axis because it's the y coordinates. So how far down? That's how far down. Goes all the way down to -infinity. So -infinity. Okay, so -infinity. Now we're going up, 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 up. Right there, there is a nice little open circle. And then there's a gap. There's a gap. Now, if there was something here and then going up, we would say, okay, it's going up, up, up. Oh, it's still there. Y coordinates are still going up, up, up. But it doesn't. So, from -infinity, it goes up as high in this interval. It goes up as high as -1. Because that right there says -1. At least it does on your paper. Okay? So, to -1. And it's an open circle. So, we're going to parenthesis right here. Are there any other intervals? So, well, there's more function up here. Okay, union something. Okay, this is down to up. Okay? So we're going to start this interval here at this y coordinate. It's at 2. It doesn't go above 2. It doesn't go below 2, but it does include 2. So we just have to say, in addition to this interval, for y values, there are points that have the y coordinate 2. Now, do they include 2? If they didn't include 2, we would not have brackets. We would have parentheses. But it does include 2. So we have brackets. All right? So 2 intervals. This interval is a single point. Right? For your range, your y values. Okay, let's move on. Your intercepts. We've talked about our intercepts in class. So, X-intercepts and Y-intercepts. Y-intercept you can find when you substitute 0 for X and solve for Y. Okay? So, the Y-intercept, substitute zeros in for X, solve for Y. The X-intercept, right? The X-intercept also is called a 0. The zeros of the function are X-intercepts, where the line or the graph touches the X-axis. We call them zeros, all right? So, this is how you find them algebraically. If I want to find X-intercept, substitute 0 for Y. I want to find the Y-intercept, substitute 0 for X. Now we're going to look at a graph. First, we're going to eyeball it. We're going to say, look at it, and say approximately, where do you think the Y-intercept and the zeros are? And then use your algebra. Do these things to figure it out. Okay? So if I eyeball this thing, my Y-intercept. Okay, well, here's the Y-axis. Where does my graph, where does this parabola intersect the Y-axis? Well, it looks like it intersects it right there. And it looks like it's at 0, 4. So I think it's at 4. It's my approximation. I think it's at 4. My X-intercepts, or my zeros, we'll call them zeros. Okay? I'll just put it 0. Where is the 0 at? There's 1 0. It touches, it just touches. Okay? We actually say it bounces off or it kisses the x-axis at 2. It looks like it's right at 2. So I think that there's an x-intercept or a 0 at 2. I think that there's a y-intercept at 4. Let's see algebraically if my estimations are correct. So first thing I'm going to do is I'm going to find that y-intercept. The y-intercepts are pretty simple for you folks. Right? I take my equation, f of x equals x squared minus 4x plus 4. But remember, I'm finding the y-intercept. So I'm going to take x and I'm going to substitute 0 in for it. So wherever there was an x, it's not going to be f of x. I'm going to find f of 0 equals 0 squared minus 4 times 0 plus 4. All right? So these are always nice and easy because all of the x's are 0. Anything with an x is going to be 0. That always leaves you with the constant. So that means my y-intercept, or my f of 0, is 4. Oh, good. Then our estimation was right on the money. Awesome. Now for the more fun one. The x-intercept. For the x-intercept, we're going to substitute 0 for y. So instead of f of x, right, instead of our y, remember instead of y, we're saying f of x. So instead of f of x, we're going to put a 0, because that is what y was. Okay? So 0 equals x squared minus 4x plus 4. Cool. Well, we got to solve this for x, right? According to this right here. We've got to isolate x. We've substituted 0 in for the y, or f of x. Now we got to solve for x. Okay, so we can factor this. Product sum. Our product has got to be 1 times positive 4, and our sum has to be negative 4. So hopefully you can all figure that negative 2 times negative 2 is positive 4, and negative 2 plus negative 2 is negative 4. So we're just going to jump straight to this. I'm going to go straight to x minus 2 times x minus 2. Okay. All right. Last thing you do, split it, and you say this x minus 2 could equal 0, or this x minus 2 could equal 0. Add 2, and you find that on both of those, x equals 2. Well, great. That's exactly what we thought it was going to be. All right, very nice. Okay, let's proceed. They give us a couple more questions. They give us graphs and they give us equations. And they say that we want the y-intercept and the zeros. We're going to do the same exact thing we just did with question 1. So visually, I look at this. My y-axis is right here. So here's the y-intercept. It looks like it's going to intercept at negative 1. Okay. And then for the x-intercepts, my zeros, there's one here, there's one here, and it looks like that's negative 5, and it looks like this is positive 1. Right? So my guess is my y-intercept is negative 1, and my x-intercept, okay, or my zeros, are at 1 and negative 5. Okay? So that's what looking at the graph tells me. Now let's take the algebra. Okay? We're going to go back to algebra 2 a little bit, do some absolute value work. So I want the y-intercept first because it's easy. So g of x, but we're going to substitute 0 for x, equals absolute value of 0 plus 2 minus 3. Okay. That tells me that g of 0, absolute value of 0 plus 2 is 2. 2 minus 3 is negative 1. That tells me my y-intercept is negative 1, just like what we thought. Okay. Again, back to algebra 2. Let's substitute 0 for g of x, or 0 for y, and we get absolute value of x plus 2 minus 3. Okay, again, this is algebra 2 stuff right here. Back to unit, oh gosh, this is unit, end of unit 1, maybe a little bit of unit 2. Okay, first step is we have to solve for the sticks, solve for the absolute value brackets. So I got to cancel that minus 3. So I've got 3 equals the absolute value of x plus 2. Okay, this is isolated. I can now split this into 2 different equations. So this x plus 2, it could equal 3 because the absolute value of 3 would be 3. Or this x plus 2 could be, what else has the absolute value equal to 3? Well, the absolute value of 3 is 3, but also the absolute value of negative 3 is 3. So we need to solve for both of these, because if we can make x plus 2 negative 3 or positive 3, the absolute value would be 3 and it would work. So we're simply going to subtract 2. So that gives me x equals 1. We're going to add 2, subtract 2 again here. And we get x is negative 5. So 1 and negative 5, look at that. We are correct again. All right? Feel free to go back, rewind that, and make sure that you can solve absolute value equations. All right. Now, number 3, square root of x squared plus 6. Right? The y-intercept. Okay, here's your y-axis right here. It looks like this point right here is somewhere between 2 and 3. Right? It's a little under 2.5. So this one's a little more difficult. So it's, I don't know, 2.4-ish. It's just a guess. And then for the x-intercepts, or the zeros, well, there's a problem here. Look, here's the x-axis. My graph doesn't touch the x-axis. Looks like I don't have any. There are no zeros. Let's see what that might look like when we solve. Okay, let's start with the y-intercept. So h of x, but we're going to substitute 0 for x because we're finding the y-intercept, equals square root of x squared, so 0 squared plus 6. Okay, well, 0 squared plus 6 is 6. So h of 0, or the y-intercept, is the square root of 6. Okay? If you want to take that, put that in your calculator, go for it. Okay? But it's pretty close to 2.4-ish. So square root of 6, that's the answer we want. This was just an approximation. Okay? Square root of 6 is the y-intercept. Now let's look at the x-intercept. Pull out the green for this one here. All right. For the x-intercept, h of x, we're going to replace h of x, or y, with 0. And now we've got square root of x squared plus 6. Hopefully you can see that a little bit nicer. The other green. Okay, so we've got 0 equals square root. Well, how do we cancel the square root? We square. So I'm going to square both sides. Well, 0 squared is just 0. Square root cancels the square. Square cancels the square root as well. So x squared plus 6 equals 0. Let's subtract 6. I got negative 6 equals x squared. How do we unsquare something? Well, with a square root. Square root both sides, we plus minus. So we got plus minus the square root of negative 6. Square root of negative 1 is I. So this is I root 6, plus or minus, for my zeros. That's not a real number. There's an I in there. It's an imaginary number. That tells me there are no zeros. There are no x-intercepts whatsoever. Okay? So again, our algebra proves that the graph is accurate, okay? So this graph definitely doesn't touch the x-axis, and our algebra says that its zeros are imaginary, which can't be seen on the real coordinate plane, right? Let's look at question 4. Same type of thing here. Looking for x-intercepts and y-intercepts. So for the eyeball test here, it looks like there are 1, 2, 3. There are 4 grid lines here between 0 and -2. So that means that each one of those little grid lines is, 1/2. There are 4 grid lines, so it should be a half for each one. So 1/2, 1, 1.5, 2, right? So by eyeballing it, I think my y-intercept is around -1/2. Okay? It looks like it goes through that grid line. For the x-intercept, it looks like there's only one x-intercept. That's right here at -2. Okay? Because this little tail here looks like it's curving off and it's never going to quite hit the x-axis. So I'm guessing that we've got y-intercept at -1/2, x-intercept at -2. Let's try it. Okay. Y-intercept, j of 0, because x is 0 for testing for the y-axis, y-intercept, equals 0 plus 2 over 3 times 0 minus 4. 0 plus 2 is 2. 0 minus 4 is -4. And -2/4 and -1/2 are equivalent. So yes, -1/2 is correct. For the x-intercept, for the 0, okay, j of x we're replacing with 0 equals x plus 2 over 3x minus 4. So you can either make this one real simple or you can get all hyped up about this one and make it difficult. All right, I have a fraction here. I've got to clear the fraction. So you can either multiply both sides by 3x minus 4, or you can do the same thing, but basically think of it as a cross multiplication. I cross multiply 3x minus 4 times 0 and I get 0. I multiply 1 times x plus 2 and I get x plus 2. Okay? Either way, if I multiply both sides by 3x minus 4, I get the same result, the same equation. Subtract 2 from both sides, and there's my -2. Okay? And we are correct again. Okay? Call us butter, because we're on a roll. Very nice. So let's look at symmetry in graphs. Symmetry, which you worked on in geometry back in the day. You had line symmetry in geometry. Okay. So if something is symmetric to the x-axis, that means basically if you fold the x-axis over, that the top half and the bottom half of the graph fold onto each other. Right? So x-axis symmetry. Okay, if this is the x-axis, fold the top half, it goes to the bottom. Y-axis symmetry. Here's your y-axis. Again, fold the right half and the left half, and they fold directly onto each other. They are mirror images. They are symmetric. The other one that's kind of cool, okay, this is the origin right here, 0, 0. On your papers, you can see that that's actually a grid. Right? And if it's symmetric to the origin, it's actually rotationally symmetric because you're not going to fold anything. But what you're going to do is, visually, if there is one point on the left of the origin, right, it has a mirror image point. That if you connected both of them to the origin, it would be 180 degrees, and they would be equidistant from the origin. So like this point here could have maybe this point as its mirror image. So if you connected them, let's put them down a little bit, to each other, you would get a 180-degree straight angle, and they would be equidistant from the origin. All right. Now, how can you tell if something has x-axis symmetry? Well, algebraically, if you replace the y with negative y and you simplify everything, you get the same equation that you started with. Right? So if you've got negative 4, 2 somewhere, negative 4, 2, you fold it down, you change the y coordinate, so the 2 would become negative, but the x coordinate would be the same. They would fold around each other. Negative 4, negative 2 would also be on that graph. And again, this is back from a page in your geometry time. So here, with the y-axis, if you change the sign of x, say we have a point right here, if you simply change the sign of x, but you keep the y the same, it's going to be symmetric to the y-axis, right? So if negative 3, 1, right, wherever that is here, is on your graph, then change the sign of x to positive 3, keep the y, 3, 1 is also on there. And then finally, if I have the point 24, right, equidistant from it and opposite down here in the third quadrant, you would have to change both the signs. We would change the x and the y. So if I change the x and I simplify it, I'm going to get the opposite of the y. So negative 2, negative 4. Right? All right, so testing for symmetry. You can look at the graph, see if it has line symmetry that's horizontal or vertical. The origin one's a little trickier because you have to, test for the equidistant 180-degree points. I mean, it's very doable, but it's just a little more difficult than simply folding something over a line for the first two, right? Support it numerically using a table of values, which we'll look at in a second. Okay, the numerical would be this right here, right? If there is a negative 4, 2, then there'd have to be a negative 4, negative 2 for an x-axis symmetry, right? And so forth. Okay, we do that with each of them. So you should be able to do that with a table. And then finally, with algebra, which is what we had right here. So this is the algebra part. Obviously, up here is your graphing part. And then right here is the numerical part. Okay? Put a little star beside that. You're going to want that before your next quiz. All right? People usually have a little bit of confusion on that part. When it asks to verify things numerically and algebraically, they sometimes mix those up. So we're going to do an example. Okay? Take really good notes on this one. Okay? As I said, this one usually bothers students, so take your time, rewind it, ask questions if you don't get it. We'll give you more examples. You're going to have practice on your homework. All right. So we're looking at this graph here, and I'm going to look at it, just analyze it as a graph. Okay. Does it look like it is symmetric to something? Yeah, it looks like if I fold over the y-axis, it looks like it. If I fold over the y-axis, it's symmetric. My eyeballs say that, okay? It says that it looks like it's symmetric. Numerically, do a little table. Okay? In order to do this properly and to prove it, you're going to need some opposites. So let's go with 1 and negative 1. 2 and negative 2, at least that much, okay? So if I substitute 1 in for x, it's negative x squared plus 6. So that would be, remember, you have to do PEMDAS. So the exponent, 1 squared times negative 1 is negative 1. plus 6. Negative 1 plus 6 is 5. Negative 1 for x. Negative 1 squared is 1 times negative 1 is negative 1 plus 6 is 5. Okay, now right now, stop and look. We changed the sign of x, and you got the same y. If you look back up the next part of the page here, that's exactly what you have to have if you are going to have a graph that is symmetric to the y-axis. If you change the x, the y stays the same. The f of x stays the same. Or in this case, you know, they didn't give us f of x, but you can imagine it's f of x or g of x. So let's just try it with 2 and negative 2. 2. 2 squared is 4 times negative 1 is negative 4 plus 6 is 2. Negative 2 squared is 4 times negative 1 is negative 4 plus 6 is 2. So there's 2 occasions where I change the sign of x, I get the same y. I change the sign of x, I get the same y. So this is backing up my assumption that it's a symmetric to the y-axis function. Okay? Confirm it algebraically. So what did we say? If we change the sign of x, so watch this, please watch this carefully. If I change the sign of x, I'm just going to leave out my x. This is the part people forget, and they lose points on that first quiz, and then they lose points on the test if they can't get it by then. All right, so instead of x, I'm going to change the sign of x. Now it's a negative x. Now I just have to remember to do PEMDAS. Okay? In the parentheses, you can't get simplified any more than negative x. Okay? You can't simplify that. Exponent, negative x squared is x squared. Okay? I'm going to bring down that negative, and I'm going to bring down my plus 6. Okay? Can I simplify this any more? No. Y equals x squared plus 6. Excuse me. Y equals negative x squared plus 6. Check that out. It's the same y. It's the same y. We changed the sign of x algebraically, and we got the same y algebraically. So on your quiz, when I say do it algebraically, all right, if you want to prove that it's a y-axis symmetry, change the sign of x, simplify it, and it better be the same y. Right? Y equals this. Y equals the same this. This is the same on both. Okay? Numerically, we change the number x. X as numbers. We change 1 to negative 1. We simplified for the y. We solve for y, bang. Y is 5. Same y. Different x, same y. Okay? All right, let's move on. We're going to analyze another graph here. xy equals 4. Okay? Is it a function? Yep, it's a function. So graphically, it does not look like I'm going to fold over the y-axis or even the x-axis. So if this thing is going to be symmetric to anything, it's got to be symmetric to the origin. So my guess is that it's symmetric to the origin. So now I'm going to use the rules that we had for symmetric to the origin, and I'm going to try to prove numerically and algebraically that it's symmetric to the origin. So numerically, let's get a little table. Right? So what does the origin symmetry say? It says if I change the x, I change the y. Okay? I change this one, it changes that one. All right? So let's go with 1, negative 1, 2, negative 2 again. Okay? You could go with 3, negative 3, 5, negative 5, whatever you want. Okay? As a matter of fact, let's change it up. just so nobody accuses us of doing the same number every time. Let's do 3, -3. Let's do 5 and -5 for x's. Okay, so when x is 3, 3 times y equals 4. Divide by 3. Y is 4/3. You say, Mr. Barry, that's not a very nice number. I don't need to graph it. I just need the number. Okay? What if I said x is -3? -3y equals 4. Divide by -3. Y is -4/3. Does that back up my hypothesis, my guess, that it's origin, rotational symmetry? Yeah, I changed the sign of x, and that changed the sign of y. Perfect. All right, so let's do the 5. Get a couple more funky fractions, make everybody happy. If x is 5, 5y equals 4. Divide by 5, divide by 5. Y is 4/5. 4/5. Okay? If I say if I say x is -5, -5y equals 4. Divide by -5. Y is -4/5. Yee-haw, we got it. Okay, isn't that great? So, I changed the sign of x, it changed the sign of y. I changed the sign of a different x, it still changed the sign of y. Okay? It's the same absolute value, but it's a different sign. Okay, so numerically, that supports rotational symmetry around the origin. Okay? It's symmetric to the origin. Let's confirm that algebraically. So we're going to do with algebra what we just did with numbers. So it said x, y equals 4. In order to confirm it algebraically, we need to say, I changed the sign of x, it changes the sign of y. So I got to change the sign of both. So I changed the sign of x, and I changed the sign of y. And if I simplify this, and it goes right back to the beginning of xy equals 4, then it is rotationally symmetric to the origin. Okay, easy peasy. What's -x times -y? Negative times negative is positive xy. That gives you the exact same beginning. So if you change the sign of x and you change the sign of y and you simplify it and you get what you started with, that means it is rotationally symmetric to the origin. Okay? All you have to remember is symmetric to the origin. Okay? For the y-axis, you change the x, you get the same y. For origin, you change both of them and you get back to the beginning. You change x and you change y. Okay? Now, say, why the heck did we just do that? This is our next application of that. Even functions are symmetric to the y-axis. Odd functions are symmetric to the origin. Okay? Here's a nice little cheat sheet for you, though. Even functions will only have even exponents. Okay? Now, a constant, like if it has 5, 5 is the same as 5 times x to the 0, because x to the 0 is just 1. Right? 0 is an even number. So if you have something like, 3x to the 6th minus 7x to the 4th plus 4x squared plus 1. Okay? The exponent for x is even. The exponent for x is even. The exponent for x is even. And this is a constant, so that's x to the 0. Okay? The 0 is even, so the exponent is even again. So that would be an even function. 3x to the 6th minus 7x to the 4th plus 4x squared plus 1x to the 0. Okay? Notice it's only the exponents of the variable that we're looking at. That's it. If they're all even, it's an even function. Here's another couple of examples here. Odd functions. If all of the exponents are odd, then you're going to have rotational symmetry to the origin. So for example, they give you here f of x equals x to the first. 1 is odd. That's cool. X to the third. X to the third is odd. 3 is odd. X to the third plus x to the first. 3 is odd, 1 is odd. Okay? Now, what about this guy? That says 3x plus 5. What are the exponents? X to the first, x to the 0. Odd, even. If it's not all odd, it's not an odd function. If it's not all even, it's not an even function. So this is neither odd nor even. Okay? Let's look at the examples of evens here. X squared, 2 is even. X to the fourth plus 5, which is x to the 0. 0 is even. Negative x squared, 2 is even. Plus x to the fourth, 4 is even. 9x to the 0, 0 is even. So these ones work. This one, x to the fifth is not, 3x plus 5 is not an odd function because you don't have all odd exponents for your x's. You have an even and you have an odd. All right. Those are the big ones, really, that have given people problems. Let's look at how easy this can be for these 3 questions. If you use the equation shortcut. Now, this says graph your equations on the TI-84, and you can do that and look at them, analyze them, see whether you think they're even, odd, or neither, and then confirm it algebraically, right? I'm going to do these the algebraic way, right? Just because I want us to be able to do the negative x's and verifying algebraically, because as I said, it's given people problems in the past. Okay, this has an x squared, right? And let's look at the algebra of it. 4x to the 0. Okay, 2 is even, 0 is even. So this tells me this is going to be an even function. Even functions they have y-axis symmetry. They are symmetric to the y-axis. So the rule on the y-axis is we change the x, and we better get our same y. So it says y equals x squared minus 4. Let's change the x sign. Okay? It says confirm it algebraically. So we're not going to make a table of a little chart with values in it. We're going to take x and change it to negative x. Okay? So it's y equals negative x squared minus 4. Let's simplify it. Negative x all squared. PEMDAS. Negative x is going to be multiplied by itself. Negative times negative is positive. So negative x times negative x is positive x squared. Bring down your minus 4. Okay, I changed the sign of x. I simplified it. It's the same y. Right? It's the same y. So you change the sign of x, you get the same y. That proves that it's an even function that's symmetric to the y-axis. Okay, let's look at this guy. The second one, x to the third minus x to the first. Both of these exponents are odd, so I'm going to say this is an odd function. That was easy. Odd functions are symmetric to the origin, so I need to change the sign of x and y and see if I go back to the original right here. So I'm going to change the sign of y, and I'm going to change the sign of x. So let me put that in parentheses. Negative x is to the third. Negative x to the first, if you want. Okay, now we just have to be careful on our simplifying. Let's simplify the right side, because the left side is as simple as you're going to get. Okay, negative to the third power. Negative times negative is positive, times the third negative is negative. So this is negative x cubed. Minus negative x to the first is negative x. Minus negative, I'm just going to write that as plus. Minus negative, I'm going to write as plus. Okay. Have I solved for y? No. Okay. I want y equals. This little sweetheart right here has got a -1 in front of it. So I got to divide this term by -1. Now I got to divide every term on both sides. Don't just divide one of them. Every term on both sides divide by -1. So you got y equals, negative over negative is positive, x cubed plus x over -1, which is minus x. I changed the x, I changed the y, and I got exactly what we started with. I just algebraically confirmed, okay? I just algebraically confirmed that this is an odd function symmetric to the origin. Okay? This last one here. X to the fourth, x to the first, 3, x to the 0. Okay? That's a 4. That's even. Excuse me, I'm sorry, that's a 3 in the worksheet. That's even, that's odd. That's odd. X to the 0, that's even. This is neither odd nor even. This is not symmetric to the y-axis. This is not symmetric to the origin. And if you did the negative x for x, it would not come out the exact same as your original. If you switch the x and the y, it also would not come out to the same as the original. Okay? Because these notes are long, we're going to stop right there because this is your worksheet. This is your chance to practice all of this stuff. I hope that this camera has done justice to being able to let you take these notes and see stuff and hear it. So I'm hoping that the microphone has worked out well. I look forward to checking this out and seeing if this video is okay to share with you. So that's what we got. That's it for day 2. Hopefully you are going to be ready for that day 1, day 2 quiz next week. Okay? See ya.